Hello everyone, I'm Giovanni Lepore. I work at the Earth Science Department of the University of Florence, and I'd like to talk to you about the first results of an ongoing collaboration with the Helmut Zentrum Berlin and Elisa Bimlein at EXAFS in Grenoble. The main object of our investigation is to study the local chemical ordering and local distortions in high entropy alloys and compositionally complex alloys. So what are we talking about when we refer to high entropy alloys or compositionally complex alloys? Well, these compounds were developed in the last century, and they represent a bit of a revolution compared to the classical concept of adding small amounts of secondary elements to a primary one. In fact, these compounds were created by mixing together multiple principal elements in relatively high concentrations in order to enlarge the compositional space available. And this strategy was already fruitful since these alloys have attracted much attention thanks to their very good mechanical properties and also good corrosion and oxidation resistance. And they're even investigated for hydrogen storage applications. Despite the importance of these materials, several basic questions still need to be addressed. First of all, the concept of solid solution in such a compound differs from that of alloys based on one principal element. Given the variability in size of the components, we should ask ourselves some questions, such as how are the different atoms distributed relatively to each other? And are they really randomly distributed, or is there an ordering of some kind? And if there are elements with bigger atomic radii, how do they distort the lattice? This is even more important since local chemical ordering and lattice distortions are frequently considered among the main actors inducing enhanced mechanical properties in materials, but very few quantitative studies are available to date. In our work, we tried to address some of these questions, focusing on local distortions and local chemical ordering in compositionally complex alloy based on aluminum, cobalt, chromium, copper, iron, and nickel. These alloys forms a single phase annealed at high temperature, known as gamma, and annealed below 900 degrees. It's shown the appearance of a secondary phase enriched in aluminum, nickel, and copper, known as gamma first. And the gamma first ratio greatly influences the mechanical properties such as hardness and ductility. The results of this investigation have been recently published on Acta Materialia. Here you can see the reference. From a basic characterization, we see that its diffraction pattern is in agreement with a simple FCC lattice, and that at all the investigated scales, the alloy is homogeneous. In order to approach this problem from a local point of view, we decided to investigate this alloy through EXAFS measurements performed at the K absorption edge of all the elements present. So what do we expect to drive lattice distortions and local chemical ordering? One of the main subsets is often the difference in size between elements. Indeed, very big atoms, such as aluminum in this case, are often added to the alloys, specifically to induce distortions. With EXAFS, we have direct access to this kind of information, since with EXAFS we can have information about nature, distance, and number of first nearest neighbors. Here, for instance, is a first shell fit at the aluminum K edge, and we notice that even though aluminum fits nicely with 12 atoms around it, with an average atomic number of 27, which is in agreement with the alloy's composition, we have a very peculiar result about the average aluminum with the average distance between aluminum and the other 3D metals, since the distance is only 2.52 angstrom, which is much smaller than what we would expect on the basis of pure metallic radius consideration, since aluminum is almost 0.2 angstroms bigger than the others. So the first important result that we have is that aluminum reduces its metallic radius in order to accommodate into the lattice and to lessen the distortion of the alloy. But with EXAFS, we also get information on the nature of the neighbors. Here we show the number of aluminum atoms in the first coordination shell of each element. And for the first time, we obtain a quantitative measurement of local chemical ordering in this kind of system, and we show that there is a strong preference of nickel and copper for aluminum. Further insights on the 3D metal preferred ordering can be inferred from crystal chemical comparison of interatomic distances, since we cannot have direct information with X-rays, since the scattering factors of all the 3D metals are too much close to each other. Here we show interatomic distance between the investigated element and aluminum in blue, and we see that these distances do not vary much, strengthening the hypothesis that there is a limited contribution of aluminum to lattice distortion. In green, we show the interatomic distances between each investigated element and the average 3D absolvers, which show some slight variation. And it's interesting to compare these measured distances with the calculated one, shown as empty circles, which were obtained by summing the metallic radius, the theoretical metallic radius of each element, with the weighted average radius of calculated transition elements in the alloy according to stoichiometry. Therefore, the distance we would expect if we assumed a completely disordered distribution of transition metals. We see that there is a reduced chromium distance between chromium and transition metals, and an enlarged one between nickel and transition metals, suggesting that there is an ordering scheme between chromium and nickel, and specifically that there is a coupling between nickel and chromium, since chromium is much more, bigger than nickel, and vice versa. So the relationship, a coupling between them, could lead to a shift of the empty circles toward the green ones. So to conclude, we show that our alloy is a single-phase FCC down to the nanoscale. We were able to quantify slight local lattice distortions, and also to see that aluminum does not contribute to these distortions. We quantified preferred ordering between aluminum, copper, and nickel. And also by crystal chemical relationship, we were able to infer some short-range ordering between chromium and nickel. The short-range ordering results that we obtain are important because this affinity between aluminum and nickel and copper in the single-phase region correlates with the aluminum-nickel copper-based gamma-first precipitation that appears below 900 degrees. And as we already said, this greatly influences the mechanical properties. Let me take the opportunity to thank the organizing committee for their work and my collaborators in Berlin and Grenoble. And thank you for your attention.